Hi guys, it's your boy J-Bug back and active, don't be kidded. So in this video, we are going to continue Physics 101. We've done useful mathematics, and so in this video I'm going to be taking you dimension. So I'm going to be taking you dimension. But before I take you dimension, there are some things you need to know. You need to know about fundamental quantities, you need to know about derived quantities, fundamental units and derived units, and some prefixes. So when we talk about fundamental quantities, we talk about quantities that are independent. They don't depend on other quantities, but other quantities depend on them. And we have seven fundamental quantities. No matter what textbooks you'll be reading, just know that for UI, for Professor Awe, we have just 7 fundamental quantities, not more, not less. 7 fundamental quantities, and those are length, mass, time, temperature, electric current, amount of substance, and luminous intensity. And these fundamental quantities have their units, and those units are called fundamental units because the units belong to the fundamental quantity. So aside from these quantities and units, others are derived units and derived quantities because they depend on these fundamental quantities. So in this video, I don't think if you guys are going to be having issues with the audio because my microphone is dead, so sorry about that. So that's that on fundamental quantities and fundamental units. We have length, mass, time, length, mass, time, amount of substance, temperature, I don't see the board clearly. Yeah, temperature. We also have luminous intensity. So these are the seven fundamental quantities you should know. All others are derived quantities, and you need to know their unit. So length, the unit is meter. So that's m for meter. For mass, the unit is kilogram. That's kg. For time is seconds. So I just need to increase my voice because there is no microphone. So just bear in. Amount of substance is mole. The unit is mole. For temperature, it's Kelvin, because Kelvin is the standard unit. So it's Kelvin we are going to use. For luminous intensity, it's candela. It's called candela, CD. And for current is ampere. A. So these are the 7 fundamental quantities and their units. Hope you can see the board. So all other quantities like maybe force, force, pressure, volume, area, those ones are derived because they depend on these 7 basic quantities. Yeah, so that's that. So let's go into dimension. So now, what's dimension? Dimension is just a way we resolve other quantities to the basic quantities. It's like as if when we have force, I want to represent force using the fundamental quantities. Like we have force. Let's say we have force. I want to show this force. We want to show it in a way that we don't want it to be in this derived way. We want it to be in the fundamental way. That's what dimension is about, and it's just resolving it into L, M, T, I, that's for ampere, the theta for temperature, the candela too, with the let's call that C, and 1, 2, 3, 4, 5, 6, and the amount of substance, let's call that mole. So it's just resolving it into these fundamental symbols. Representing the derived unit is a fundamental symbol. But you know this is mechanics. So in mechanics we are just going to be dealing with only these 3 LMT because it's length, mass, time, because it's mechanics we are dealing with. So there are some basic examples. There are some quantities you need to know their dimension offhand. Like you don't need to prove those stuffs. There are some like You need to know the one for velocity. You need to know the one for acceleration. Is velocity. You need to know the one for acceleration. Acceleration, yeah. Especially these two basic ones. Yeah, you need to know the one for force too. You need to know the one for force. So I already know these ones offhand, but for for me to teach you, for you to know it, you need to know how to derive it. So what's velocity? The formula for velocity. Formula for velocity is displacement over time, right? So when we have displacement, this displacement, let's call displacement d over time. Let's call that t. Now, if we look at it, displacement is a fundamental quantity. Why? Because displacement represents length. Because it represents distance, and distance is a fundamental quantity. Distance, length, you understand? They are together. So displacement is a fundamental quantity. That means we are going to leave it as d. And in fundamental quantity, the symbol of distance or length is L, right? So that will be L over t. T is time, and the time is also a fundamental quantity, and the symbol is capital letter T. So that will be T. Understand? So the dimension for velocity is L over T, but we won't leave it in this way. We are going to leave it in the standard way that we all know. And we know if something is like this, if T is on the bottom, it's just like it's still writing like this. This is still 1 over T. Writing things like in the indices form. So this will be L T raised to the power minus 1. Understand? So if you have let's say a raised to the power minus 2, that will be 1 over a square. It's just indices. That's why using mathematics is useful in mechanics. So that's that. So this is the dimension for velocity. You need to know this one offhand. Understand? So you won't stress yourself. So for acceleration is velocity over time. Over time taken. So that's v over time. So we can just do this one quick, because since we know the dimension for velocity, we can just input it inside. So that would be L t raised to the power minus 1 over dimension for t is a fundamental quantity, over time t. That would be L in indices. If minus 1 divided by 1, that would be minus 1 minus 1, because there's a 1 here. That would be minus 1 minus 1, because the division that is separating them. If multiplication needs to be plus, if division is minus 1, minus 1 minus 1, that would be LT raised to the power minus 2. So that's for acceleration. So you need to know this one too offhand. And for force, let me write it. For force also, you need to know this one offhand. What is force? The formula for force is mass times acceleration, right? So that's mass times acceleration. Mass is a fundamental quantity, so we are going to represent it as m. But acceleration is a fundamental quantity, so we need to represent it in the fundamental symbols. And that will be, since we already know the dimension for acceleration, let's just input it straight. So that's L t raised to the power minus 2. So the dimension for force is m L raised to the power t minus 2. So that's just the easy way of getting the dimension for any quantity. There are also lots more. For viscosity, also know viscosity offhand. Viscosity is this one comes out in tests. but they will give you in a very tricky way. But just know that viscosity, the dimension is constant, and that's ml raised power minus 1 to raised power minus 1. This is the dimension of viscosity. This is the dimension of viscosity. So just know these ones offhand. If you ask you for the dimension for volume, you know volume is area times height, area is length times length. That's L cube. So the dimension is going to be L cube. They can ask you for this one is common. This one is common. Okay. So we all know this formula. This Isaac Newton formula, where the force on a body in a space is directly proportional to the product of the masses and inversely proportional to the distance separating the two bodies. You all know this formula. F is equal to gm1 m2 over r squared. Then they will tell you what is the dimension for this gravitational constant. So let's derive it. If they ask you what is the dimension for this g, what is the dimension? So it's easy. Let's just make g the subject of the formula. That will be g. Can you see? The g will be f r squared over, let's just say, a meter times mass times mass is the mass, so that's mass squared. So if we look at this will be force. So the dimension of force, we need to know this one often. The dimension of force is m l. Let me write degree. So the dimension of force is m l t minus 2. M L T minus 2 times r squared. R is radius, and radius is also length. So you can just represent it with L squared over m squared. That's mass. So that's m, capital letter m squared. So if you just take out the common stuff from the numerator and the denominator, we get m will be here. I think that's all. So we are going to get the answer of the m, because this one is in the denominator, it's going to be minus 1, because it's as if this one is m raised power 0, so 0 minus 1 is minus 1. So times the length, L times L, that's L raised to power 3. L raised to power 3 times the time is t minus 2, t raised to power minus 2. So the dimension for g is equal to m minus 1, L raised to power 3, t minus 2. Listen, they even ask this stuff, they ask it in JAM, in post-term, and they also ask it in 100 level. They will ask it in 100 level in the test or exam. So, but what I used to advise is to be fast with answering questions. It's good to know how to derive it, yes, but to be fast in answering questions, just memorize it. Because that's what it's good to be. It's good to know, and sometimes it's good to be smart. So memorizing this thing will make you like answer the questions faster. But you can know how to derive it. So in case you forget, you just derive it in the test. But most times, just memorize it. So this one is a common question too. So that's that. Now, so there's what we call the usefulness of dimension. It's say to prove if an equation is correct and to show the dependency of a variable. So there's this question where they'll give you, let's use this one, v is equal to u plus 80. V is equal to u plus 80. Then they'll say show that this is a correct equation. So to show we use dimension to show if an equation is correct. And using this, there's this principle we call principle of homogeneity. It states that the dimension of two quantities are going to be equal if they are either separated by this sign is equal to or by plus. Understand? So in this stuff, so that means in this equation we can say v is equal to u. We can say v is equal to 80, and we can say u is equal to 80, because these two, they are separated by plus. These two, they are separated by is equal to. These two, they are also separated by is equal to. But we cannot say a is equal to t. Why? Because a and t are separated by a product sign, like by multiplication sign. So we cannot say that. So to prove that this equation is correct, you just have to look for the dimension of it. So v, the dimension of v is velocity. The dimension of velocity is lt raised power minus 1. The dimension of u is also velocity, lt raised power minus 1 plus acceleration is lt raised power minus 2 times t times time. So that will be lt raised power minus 1 is equal to lt raised power minus 1 plus, in indices, t raised power minus 2 times t, that's minus 2 plus 1. There's a 1 here. That will be, this is going to be lt raised power minus 1. So you can see it's still the same thing. Since this one is equal to this one is equal to this one, we are correct. That means the equation is a standard equation. Blah 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 blah. So there's this question in the slide. I can't really remember the question, but the question is like this. Where do we say x? Let's say x is equal to a plus, let's say a plus b raised to power, let's say t minus 2. I will say y is equal to, let's say c raised to power c times, let's say ct plus d. Let's just give, the question is like this, but this is not the exact question, but these are it. So they say you should find the dimension for, they say find the dimension for a, b, c and d. It's easy, very easy. Why? How do we find the dimension? In principle of homogeneity, they say the dimension is going to be equal if separated by is equal to or plus. The dimension of a, okay, and we'll say here, the question will say x and y, they are displacements. X and y are displacements. And we all know that displacement is a fundamental quantity and represented by length L. So if they say, what is the dimension of a? The dimension of a will just be x. A is equal to x. Since they are separated by this equal, so a is equal to x. That will be a is equal to L. B. How do you get one for b? We can say b t raised power minus 2. All these ones here, they are equal to a, and the dimension of a is L, as we've gotten from here. So let's say b is equal to L over t raised power minus 2. That will be b is equal to lt squared. You feel me? Because these t raised power minus 2 are the denominator, so it's as if we have this invisible 0 here. So we have is 0 minus 2. That is 0 plus 2. That's lt minus 2. It's just simple indices. So that will be b is equal to lt squared. Understand? So we've gotten for b like that. For c, how do you get for c? This ct. We can say y is equal to ct. You can say y is equal to ct. That's, if since y is equal to ct, then c will be equal to y over t. What's the dimension for y? L. That's because since it's displacement, so displacement in the y axis. So that's L over t. As c is equal to lt raised power minus 1. And for d, this is just simple. Since y and d are equal, they are separated by is equal to sign. Since y and d are equal, that means d is also equal to L. Feel me? So that's just, it's very easy. There are also some complex examples. Before the test, we are going to solve some questions. Like I'm going to solve some questions and one page. I don't know. Yeah, and most of some people are like saying I should teach math 102. I can't teach math 102. So, but if I get someone that can teach math 102, of course, there will be a video on math 102. But for now, just physics, chemistry, and biology. I've never started biology, but physics, chemistry for now. So, what else do we need to know about dimension? I think that's all we need to know about dimension. Okay, yes, before I continue, there's what we call prefix. There's still one I need to solve, that variable to show usefulness of dimension, to show how variables depend on each other. But before I continue, there's what we call prefix in physics. When we have kilo, mega, giga, tera, and peta, stuff like that. So let's say we have this is something. I don't want to waste space. So let's say 10 raised to power 3, 10 raised to power 6, 10 raised to power 9, 10 raised to power 12, and 10 raised to power 15. I also have 10 raised to power minus 3, 10 raised to power minus 6, 10 raised to power minus 9, 10 raised to power minus 12, and 10 raised to power minus 15. So the ones that does not have the minus are the ones that are big. They are big, of course. 10 raised to power 3 is 1000. 10 raised to power minus 3 is 0.001. 1000 is very, very bigger than 0.001. So these ones are called the super units, and these ones are called the sub units. There's a video I uploaded on my channel where I taught you how to convert from super unit to sub units and vice versa. It's called the chain link conversion method. I did it in my video, but the visual was not clear. That was my old camera, so the visual was not clear. So you can rewatch the video. If you follow very well, you will understand. But I'll just solve just one example. I solved a lot of examples on that video, but here I'm just going to solve just one example. So what do we call 10 raised to power 3? 10 raised to power 3 is called 10 raised to power 3 is called kilo. It's not like this. 10 raised to power 6 is called mega. 10 raised to power 9 is called giga. 10 raised to power 12 is called tera. And 10 raised to power 15 is called peta. And they have this symbol. Kilo is K. Their symbols are always big, so that's how to recognize it. Kilo is K, mega is big M, giga is big G, tera is big T, and peta is big P. So that's how you know them. Why for this our sub units? 10 raised to power minus 3 is milli. Then this one is small letter M. 10 raised to power minus 6 is micro. This one has the symbol of mu, like that one of coefficient of friction. 10 raised to power minus 9 is nano. That's small letter n. 10 raised to power minus 12 is no. This one is femto. 10 raised to power minus 12 is pico. That's small letter p. And 10 raised to power minus 15 is femto. Mind you, there are like there is 10 raised to power minus 24. They also have their own names and stuff like that. We have exa, we have yocto, we have zepto, we have zeta. But for your 100 level, this is what you are going to need. Anything outside this thing is not going to come out. As I used to say, anything outside from a slide have a very, very tiny slim chance of coming out. So this is the thing you should know. So this is the stuff you should know. So So let me solve just one example on what I said I was going to solve. So which one should we use? Okay, let's do this. Let's use and beta and oops, let's use beta and nano. So if they say convert, so I want to show you how to convert from one unit to another. I'll convert from a super unit to a sub unit. You can also do it all around. It's very easy. You know, in the example, you just want to times this, you might get it, but the chances of missing it is very high. So here now, you say times power. Let's say we want to convert beta to nano. We use what we call the chain link conversion method. I'm always lazy to write long words, so let me just put it the chain link conversion method. So let's just call it CLCM, chain link conversion method. So let me clean it because of space. So, but just know it's called chain link conversion method. So let's say they say you should convert 5 petameter. These are going to write 5 petameter to nanometer. Look at it. 5. Can you see the board? Yeah. So 5 petameter to nanometer. How do you do it? The first thing you need to know the value of peta, and you need to know the value of nano. If you don't know the value, you're not going to get it. So you need to know the value of peta. You need to know the symbol, how to recognize the symbol. Anything big letter is for the super, anything small letter is for the sub. So this is a big P. Let's say it was a small P now, you are called a pico. But it was a big P, you know it's peta. So that's peta. Nano, small n. So how do we convert it? We know peta is 10 raised to the power 15, and we know nano is 10 raised to the power minus 9. You should also know that. So this will be it. 5 petameter is 5 times 10 raised to the power 15 meter. And we know, so you know 10 raised to the power 15. Peta is 10 raised to the power 15 meter. 10 raised to the power 15 meter. While nano is 10 raised to the power minus 9 meter. Just write this one somewhere. So the aim of this thing is that we want to cancel. We want to cancel everything in a way that is going to remain just nanometer. So here now I want to cancel. It's going to remain nanometer, right? So here now I want to cancel peta. So we'll divide by. Let me clean this one up. So we'll divide by. I want to cancel peta, so we'll divide by 1 petameter. So okay, let's write it this way. How come? Let's write it this way. 5 petameter to nanometer, right? So this is 5 petameter. Once you represent everything in a way that you cancel everything out, just remain only nanometer. So to cancel out petameter, we'll divide by, I will say 1 petameter is equal to 10 raised to the power 15 meter. 10 raised to the power 15 meter. And times, so we've cancelled peta like this. And 10 raised to the power minus, that's 1 nanometer. As 1 nanometer is equal to 10 raised to the power minus 1 nanometer, 10 raised to the power 10 raised to the power minus 9 meter. So what we just do is just cancel petameter. This here, cancel petameter, meter will cancel meter, will cancel meter. Then multiply everything together. Do you understand? I think I should go back. Let me go back. So I want to carry everybody along. So if they give you a question like that, the first thing you should know is know the symbol, know what it represents. This is representing peta, this is representing nano. Know the value. Write it down somewhere. Peta is 10 to the power 15 meter. Nano is 10 to the power minus 1 meter. Now write 5 petameter, because that's what we want to convert. We want to convert 5 petameter to nanometer. So this chain link conversion method is just that this is what it means. We want to cancel everything out in a way that is going to remain only nanometer, because that's our destination. That's where we want to reach. So we're going to cancel everything in a way that is going to remain only nanometer. So we want to cancel petameter because we don't need it. So we want to divide by petameter. So then we have to divide by petameter, because with petameter I'll cancel petameter. So we'll say 1 petameter. We'll put petameter down is equal to 10 to the power 15 meter. 10 to the power 15 meter times. We also want to cancel this meter. So we'll now say 1 nanometer. We are getting to nanometer. So we'll now say 1 nanometer is equal to 10 raised to the power minus 9 meter. You understand? We position this thing in a way that you cancel everything out, and after cancelling everything out, it remains only nanometer. Now see, look at the magic. Petameter cancel petameter. This rule this. You can see meter cancel meter. Meter rule this. Now what unit are we left with? Only nanometer. See, we are left with only nanometer. This has cancelled this. This has cancelled this. We are left only nanometer. You can see, very easy. So just multiply all the values together. As 5 times 10 to the power 15, 10 to the power 15 times 1 over 10 to the power minus 9 times nanometer. 1 nanometer. 1 nanometer is 1 nanometer. So when you do that, you get 5 times 10 to the power 15 minus, because this one is in the denominator. So 10 to the power 15 minus 9. Now 10 to the power 15 plus 9. And 15 plus 9 is 24, right? If I'm correct, yeah, I'm correct. 15 plus 9 is 5 times 10 to the power 24 nanometer. You can see, right? Oh, you can't see. 10 to the power 24 nanometer. Okay, you can see here. 10 to the power 24 nanometer. Look at it. Yeah, so that's how we got 10 to the power 24 nanometer. So this is what the chain link conversion method is. If you want to see other examples, how to convert from meter per second to kilometer per hour to convert kilometer per hour, you can watch that video. I'll put it around this place, so you can click on it. And so that's all. So most people, to convert from kilometer to meter per second, you just know multiply by 1000 divided by 36 times 36 by 60 times 60. But it's more to that. It's just like this. So, don't cram any formula that 1 nanometer is equal to this, then you start cramming everything at 1 nanometer, you just bust your brain. When you know this method, I'll be to it. So I think that's all on dimension. Okay, there's this stuff. This one does not really period. When they did the experiments, they noticed that period depends on mass, depends on length, on mass of the ball, length of the string, and depends on acceleration due to gravity. You understand? The acceleration due to gravity varies on the pole and the equator and stuff like that. So then they got to, so after they found out it depends on this, then that's T is equal to kmlg, because there has to be a constant in variation. But this constant is dimensionless. A constant is dimensionless. So, and dimensionless quantities are also called pure numbers. So this one will not be there. You just erase it because it's dimensionless. So that would T is equal to mx, l raised to power x, and g. Sorry, let's represent this one with y, and let's represent this one with z. Why we raise them to the power? Because in dimension has to be raised to the power. It has to be raised to the power. So even if it's LT, you see it is still like this. So, but we don't know the power. So that's why we represented it by x, y, and z. So moving forward, m raised to power x. Mass is a fundamental quantity, so it's just represented as m. Length is a fundamental quantity represented as y. But this g is acceleration. And acceleration is velocity over time. We all know the. So that will be L t raised to power minus 2 all raised to power z. So the period t, have m raised to power x, l raised to power y. That if you expand this bracket, you get l raised to power z and t raised to power minus 2z. Let me change from the top part. T raised to power minus 2z. So can you see it? So t raised to power minus 2z. So after this, we're going to look for a way to simplify everything. So then that's when we move to indices back. Collect like times m raised to power x is here. But looking at it, L and Y, L and L. So when we multiply, that will be times L raised to power Y plus Z, right? Like y plus Z times t raised to power minus 2z, t minus 2z. So after that, we want to multiply. We want to equate all the raised to power on the left to the one on the right. So when we do 2, t this one here, so minus 2z is equal to 1, as z is equal to minus half, right? On the left hand side, you say y plus z is equal to 0, because there's no length at the left hand side, so it's still something like this: l raised to power 0, m raised to power 0, because l raised to power 0 is still 1, m raised to power 0 is still 1, and 1 times t is still t. So it's just like this. So y plus z is equal to 0. X, that's for mass, x is also equal to 0, as there's no mass on the left hand side. So after doing that, we found our value for z, right? We found our value for x. What's our value for y? So we just use substitution method. Since z is minus half, as z plus y plus z is minus half, as y plus minus half is equal to 0, as y minus half is equal to 0, as y is equal to half, as y is equal to half, right? Y is equal to half, right? So that's that. Let me erase this since we don't need it again. So let me just write it somewhere here. X is equal to 0, y is equal to half, and z is equal to minus half. I hope you guys are following. So since we've gotten the values for the x, y, and z, we've gotten the values of the exponents out of the raised to power. The exponents, we've gotten the value of the exponents. You just have to impute it into this m raised to power x, l raised to power y, and g raised to power z, right? So that will be t is equal to k m raised to power x, l raised to power y, and g raised to power z. So what's x? X is 0, right? That's m raised to power 0. L, what's y? Y is half. from here. So y raised to power half, and g is minus half. Minus half. So let me write here. So simplify further. This k we are looking at is a constant, and that constant is represented by 2 pi. So write it there, 2 pi times m raised to power 0 is 1. Anything raised to power 0 is 1. 1 million raised to power 0 is 1. Raised to power 0 is 1. So raised to power 0 is 1. So m raised to power 0 is 1. No need to write the 1. L raised to power half is square root, because x raised to power half is the square root of x, right? X raised to power 1 over 3 is equal to the cube root of x. We just simply indices. B raised to power 1 over 4 is equal to the fourth root of b. You understand? So if you understand that, then you don't have problem. So here now they said L raised to power half, that's square root of L, dot, this one is now G raised to power minus half. If you forgot, when we have, let's say we have x raised to power minus half. Yeah, let me start from the simple one. Let's say we have x raised to power minus 1. That's 1 over x, right? Now we now have x raised to power minus half. We know x raised to power half is square root of x, but now there's a minus there, that will be 1 over square root of x because of this minus. Understand? I just hope my voice is loud enough, because the microphone is dead. It's not even bringing light, so the microphone is dead. So g raised to power minus half is 1 over the square root of g. I think we are getting somewhere. 1 over the square root of g. So when you simplify this further, you get t is equal to 2 pi square root of L over square root of g. And to make it simple, that's how we got t is equal to 2 pi square root of L over g. That's how we got this formula. I hope you now understand how we got this formula. And that's how they got most formulas using dimensional analysis. So that's that on dimension. I think that's everything on dimension. That's everything on dimension. Yeah, that's everything on dimension. That's everything on dimension. All we now need to do is solve more questions for the upcoming test. Likewise, we need to solve more questions for the upcoming test. So that's everything on dimension. I'm going to be filming vector right now because I want to film all the videos I want to do, so I can also prepare for my test.